Get started. We left off last time after discussing switching losses. We said that we would now want to go and design, the thermal system that's around the switch, right? So to do that, we came up with or discussed. I quickly put up this equivalent circuit, saying that it resembles the thermal equivalent circuit of the switch that we're using placed in its environment. Okay, so one important equation that we will typically use or that we will need to use is the equation that governs the temperature of the junction at the junction of the device. Right. This is the most critical criterion that we want to satisfy. We looked at the data sheet last time and we saw that there's a junction temperature maximum value that is given in any data sheet. So you will have a maximum junction temperature for operating, and you will have a maximum junction temperature even for storage of the device, right? So typically this is a very important thing to consider to calculate every time you do a design. So how do you come up with this value for this temperature? So this temperature at the junction, again, we said the junction is basically the silicon junction of our actual physical die that's inside the package that we have, right? This package at the end can also be mounted on a heatsink if needed, right? If needed means if the junction temperature now is too high, you will need to find a way to reduce the junction temperature. So how do you reduce the junction temperature? We will find that to reduce the junction temperature, we will have to reduce these drops. So we said that this equivalent circuit resembles what? This is the power loss that we've calculated. All the power loss that we've calculated, switching, conduction losses, turn on, turn off, and conduction losses. This will be like a current source. And then we have this couple of resistors in series. These resistors in series will resemble the resistance to heat transfer from the junction. So if heat can be easily dissipated from the junction to ambient, right, there will be some resistance there. So the thermal resistance is typically given in degree C per watt. So I'm able to, the heat sinks, for example, will be able to dissipate a certain amount of degree C per watt of losses, or the device temperature will increase by a certain number of degrees C per watt of loss, right? So I have a device. This device has power loss going through it, right? This is power loss generated inside it. This power loss will cause the device temperature to increase. Increase above where? Above ambient, right? Above the ambient conditions. I mean, if we start, it's at 20 degrees C here, right? Any heat loss generated inside the device will increase the temperature of the device above ambient, correct? So the equation that resembles this circuit is what? Tj is equal to what? Equal to the power loss times the thermal resistance, total thermal resistance, plus T ambient, right? This total thermal resistance, I can divide it up now into total thermal resistance between junction to case, total resistance between case to sink, total resistance between sink to ambient, right? So I have my junction here. It does have heat generated at the junction, right? This junction is going to try to dissipate heat to the case of the device, right? So there's a thermal resistance, there's an impedance to heat flow between the junction and the case, right? And then this case, you can leave it up in the air, just hanging out there with no heatsink, for example. Or this case can be designed with a thermal pad in the back to improve, for example, thermal conductivity and dissipation of the heat to the ambient environment. Or this case can be put on a heatsink, right? And this case can be put on a heatsink with thermal grease in the middle. or it can be put on a heatsink with another, thermally conductive, electrically isolating material, right? Because if the case has a metal pad in the back, the metal pad is actually a live electrical terminal. So you cannot just put grease. If it's a completely plastic case, yes, you can just lay it on the heatsink. No problem. A heatsink is metal. This is a completely plastic case, insulating case. You can put it there, and it will dissipate the heat. But there are some cases that have a metal pad in the back. These metal pads in the back are actually electrically conducting. They're actually connected to one of the electrical terminals. So you cannot just put it on a heatsink. And you cannot just put some grease and put it on a heatsink. You have to put electrically insulating, thermally conductive, a sort of sheets, like a piece of paper. But it's a good thermal conductor and electrical isolator, right? So depending on what the case looks like, if it's a metal case, you definitely have to always isolate it, electrically isolate it. If it's a plastic case but with a pad, you have to electrically isolate. If it's a plastic case, pure, you don't need to electrically isolate, right? So then we can play with. So there are certain ones of these that you can play with. So the junction to case I cannot play with really, and the case to sink, you can sort of play with the grease that you put in there, or that thermal sheet that you put in there. That sort of can govern this. The sink to ambient is something that you can play a lot with. The sink to ambient is something that if you don't put a heat sink, if you don't put this device on a heat sink, this sink to ambient will be a huge number, right? There is a huge impedance to heat flow from the sink of the device. If you don't have a heat sink at all, it's a big impedance, right? Or if you have this device just, for example, laying on a heat sink without proper thermal grease, for example, there is still quite a bit of big resistance to heat flow from the sink to the ambient. Yeah. So if you put a proper heat sink, if you size the heat sink properly, you will find that this resistance will typically be something in parallel, right? So if this is originally with no heatsink at all, this is a large number, right? If you just have the device hanging up in the air, like you see lots of boards would have the device there and there's no heatsink. It's a cost, it's an additional cost as well as size. So if you don't need it, you don't put it, right? So sometimes you don't need it because the power loss that's in the device is minimal, right? If the power loss in the device is minimal, it's not gonna cause the temperature to rise because the power loss is this current. If this power loss is very small anyway, right? The current is small, fine. This is a big resistance. This is a big resistance. This is a big for example, even if these are big resistances, the power loss is very small. So the temperature here will be low, right? The temperature is equal to the ambient temperature plus the drop across these resistors, right? Which is due to the current, the current analogy, which is the power loss, multiplied by the sum of this thermal resistance. Typically, the junction to case is a small value. Right? Typically, it's a small value because again, it's very close. They're very close to each other. Typically, it's very close. And then the case to sink. Typically, if you have a heat sink and you take the case and put it on the heat sink and screw it down properly, you will still have a low case to sink thermal resistance, right? If you add some grease, you improve that a bit. You get a better thermal grease, right? So it's thermal grease that will help conduct the heat. So you have a smaller case to sink thermal resistance as well. And now, okay, the heatsink itself. This heatsink can be a sheet that's this big, or a sheet that's this big, or a finned heatsink, for example, that you've worked very hard to increase the surface area, right? Heat dissipates better for a larger surface area. That's why these fins are there on heatsinks that you may see, right? It's all of this surface area between the fins can help dissipate the heat, right? So if you compare this versus just a sheet of the same size as the top part of the heatsink, this is a much better way to sink the device because of the surface area that you have here, right? So this sink to ambient, you have a lot of control over, right? So typically it's a large number if you have a poor heat sinking method, or if you're not heat sinking at all, right? And then anytime you do something there on the heatsink design, you add a resistance in parallel. Okay? If you add a cooling system, it's resembled as a resistance in parallel because it's going to improve the thermal resistance from your sink to ambient. It's at the end of the day, it's the thermal resistance between you design a, actually the way you design a like a cooling system for a device would be based on the equivalent thermal resistance of that device. I would like to design a cooling system for the vehicle. Fine. What is the thermal resistance from the engine block to the ambient before and after putting that thermal cooling system that you've added? That's the number that you design the cooling system for. Okay? So here, if this is a large number, like let's say 100, and I've designed this to be 10, these two resistors are in parallel, right? Which would be more dominant? The small one, right? You have two resistors in parallel. What's the equivalent value of resistance? The smaller one, right? And if you have 100 ohms and 1 ohm in parallel, what's the equivalent value of resistance? 100 times 1 divided by 101, right? So it's the small, it's 1, correct? So that's why we would resemble this a better heat sinking process as a resistance in parallel with the sink to ambient resistance, yeah. As a first degree, right? So maybe you maybe just find a full equivalent to that if you want to go into more detail. But just as a simple approximation, that's what it is basically. So these will be the numbers. Sometimes they're on the data sheet. So I don't think I have my Wi-Fi on. That's why. Let me turn on the Wi-Fi. So if we go down to the data sheet that we have for the device here, you will see here, there's a whole section on thermal design in the data sheet. They will give you the junction to case to sink, or case to ambient if you don't have a heatsink, right? If you're just going to have your device up there without the heatsink, then it's the junction to ambient thermal resistance that you care about, right? It's that the sum of these three is the junction to ambient. So here they gave you here the data for the case where you will put a heatsink or without a heatsink. Without the heatsink, this is the junction to ambient thermal resistance. It's what? 62 degrees C per watt. So every watt of loss will increase my junction temperature by 62 degrees Celsius. Okay? That's why it's crazy. I mean, if you have 5 watts of loss, then 5 times, it's like 300 degrees Celsius, right? You cannot operate that way, right? So, but this device, if you operate with 1 milliwatt of loss, it will survive. Will it survive? You go to your equation. T junction is equal to thermal loss, thermal resistance times the power loss plus the ambient temperature. This is like 25, for example. Let's say this is 25, for example, and then this is what, 62. So if you have 1 watt of loss, you're talking about 62 plus 25. So you're talking about 87 degrees Celsius.
Do they have chips that, like, whenever they get too hot, it like basically shuts down?
Yes. Yeah. So there are chips that have internal thermal shutdown. Yes. So obviously for downhole stuff, we cannot use that stuff. In applications where the temperature will be high, you will never be able to use these kinds of chips. Yeah. So what we end up doing in applications like this is we screen everything. So, and you can actually buy the same components from the vendor, screened to a higher temperature. So there's lots of stuff that can be done. But again, we're talking about from a commercial application perspective. Yes, there are things that would shut down at temperature. Yeah. So that's the value of this equation. Does everybody see the importance of this equation? So here we put with 62, we see the temperature is 85. 85 is okay. And if you go look at the junction temperature here, the operating junction and storage temperature is up to 175 for this chip. So this device can still survive up to 175. But is it going to survive beyond 175? No. According to the data sheet, beyond 175, you should put zero current through it. It will not be able to survive. This is the maximum operating temperature of the junction. Okay? So if you find that your power loss will push you close to that, and we know, is our power loss an accurate calculation? It's not. I said that we are going to put some triangles so that we make our life easy to calculate. We ignore, whether you include or not the time delay, the turn-on delay versus the rise time, the turn-off delay versus the fall time. Fine, it's okay. I mean, it's an approximate number anyway. Just take their average value, or take a number, or take them both. As long as you show me what you're doing, I'm happy, right? And you'll get a ballpark figure. But this ballpark figure is plus minus 25%, for example, right? So if you end up with, a junction temperature of 120 for a device like this in ambient, I would probably put a heatsink or start reducing my switching frequency, or reduce my conduction loss, or do something. I have to do something about it, right? So if you find that it's too close, then you have to go another route. You cannot go with the route of purely having the device hanging in the air without a heatsink. Then in that case, you will need the junction to case thermal resistance that they have here, junction to case thermal resistance, and then the case to sink thermal resistances. These are really small, right? Typically 0.5, maximum 0.7. So both of them together are about what? About 1 degree C per watt, right? So 1 degree C per watt versus 62, right? That's a huge difference. But of course, this does not include the sink to ambient. There's still, this is the junction to case, and then case to sink. It's only from the junction to the case, and the case sitting on a sink. What sink? Right? The sink is what you have to go buy. You will buy heat sinks or have a cooling system or add a Peltier tube or whatever you want to do. It will have a thermal resistance, and this thermal resistance is what you plug in series with the 0.75 and the 0.5. Right? So I don't know if I have the thermal resistance of the heat sink here. Yeah, I do. Here, board level heatsink. So this is an example of a heatsink for a device. Actually, not for this power device. It's for a smaller device. Yeah, but here, for natural convection, meaning you just buy this heatsink. This heatsink is nothing but a piece of metal. It's a very small heatsink. It's a piece of metal, basically. Yeah. Not even thin. I mean, it's a very small. The picture is not very clear here, but. You put the device down here, and it's just a piece of metal around the device. I don't know if you can see it clearly. I don't know, it's not clear, but the device is here, and it's just a small box around the device, basically, that you screw the device onto, and it will just fine. It will increase the surface area, hence reduce the case to sink ambient thermal resistance, right? But of course, it's not a big finned heatsink, or it's not a cooling system, right? So what we see is on the data sheet, they will give you the thermal resistance for that heatsink. So let's say I choose this top one. This is the heatsink I chose, 21736, blah, blah, blah. It will have a thermal resistance of 55 degrees C per watt, right? So 55 and then 1, that's 56. So 56 versus 62. Is it worth buying a heatsink or not? You have to decide, right? In this case. But if I force convect the air around the heatsink, so I put a fan, for example, right? Like in processors or computers, you'll find a fan at the end of the so that's forced convection, right? That's not natural convection. Natural is just I have the heatsink naturally convecting the heat out to the ambient environment. Versus forced convection is you are pushing water, you're pushing air, you're pushing whatever. Okay, it's you will have to read more about what they mean by forced convection. But under forced convection, yeah. So this is forced convection at a certain amount of speed of fluid around it. So liters of fluid per minute or something like that. Okay, I'm not. We would have to look at this in more detail. But if you are pushing this amount of fluid around this specific heatsink, its thermal resistance will go down to 16 degrees C per watt. Right? So now you have to optimize. Do I put this heatsink with forced convection and keep the same device even though the power loss is a lot, or do I go with a different device, or do I just allow the power device to get hot because I want a small package and I want it to be very cheap, right? So that's part of the design process here, right? So you have this heatsink data sheet there to help as well, yeah. Okay. So any questions on this? It's a simple equation, but there's a lot of insight, and it's very important in the design process. Yeah. So this simple equation is I mean, again, this is the ambient temperature 25, thermal resistance is the sum of these three. They don't have to be three. Okay, they don't have to be three. They may be just the junction to ambient, like they gave you in this data sheet. If you're just putting the device in ambient, if you're putting the device on a heatsink, then you will have to divide it up into the three. Sometimes some data sheets, by the way, they don't give, for example, they would give the junction to ambient only, right? But the device is packaged in a certain package. So you would have to do some more Google searching to find out what is the typical junction to case temperature for this type of package, right? Because again, at the end of the day, it's these surface mount packages, they're very similar, right? So the thermal resistance between the actual die and the case itself is very similar in all these types of packages. So sometimes if you don't have enough detail in the datasheet itself, doesn't mean that you cannot find that information. It means that you have to dig more as a designer to be able to find that proper information that you need. So in this datasheet, they helped you a lot. They gave you the junction to case and the case to sink, and then you need to figure out the sink to ambient. They did not give that to you because they assume that if you need this detail, you would design a heatsink around the solution, right? So any questions on the thermal design stuff? I mean, it's a direct substitution. I mean, they have some examples on page 453 in chapter 10. With some direct substitution. I mean, really, really simple direct substitution. So I'd recommend just going through one or two of these examples on page 453 and 452, 453. And the discussion starts at 451. So the discussion starts from just 3 pages. Page 451 through page, I would say, beginning of page 454. So then they get into the thermal dynamics of the thermal process, right? So the device is turned on, so there's more heat, and then there's turned off, there's less heat there. Then they try to look at the average value, and then they try to find the dynamic equivalent circuit for the thermal process. We're not going to get into that, okay? We want the first order approximation of the thermal process so that we can select the heatsink. If you want to optimize your device, your system even more, then fine. Dynamics are important. You want to see how fast the heatsink will help the device reach steady state, right? Because if the heatsink is very big, right, this is a thermal mass, right? The larger the heatsink, the larger the thermal mass that you are sort of heating up, and they compare that to a capacitor, right? The larger the capacitor, the higher the amount of charge needed to raise the voltage of the capacitor, right? But then when you're at steady state, your voltage is steady, right? And then you need just small charges, input and output, to be able to maintain the voltage where it is, right? So same thing with the heatsink. The heatsink is a thermal mass. At the end of the day, they compare it to a capacitor. So at the end of the day, to reach a certain temperature and will stay, that's the steady state temperature of the device. We are sort of forgetting about that. We're looking at the steady state operation of the circuit anyway, right? So we're not looking at adding capacitors in this circuit here. This is more than enough for a power electronics person to begin the design process. So any questions on this? Okay. So we have, what else? So we looked at, we looked at the performance of the boost converter when we had a resistance in series with the inductor, right? So when we wanted to include the copper loss of the resistance, we looked at the performance of that when we were studying the boost converter. I think we looked at that here, right? We looked at the effect of adding RL in the boost converter, the resistance of the copper wire to the inductor. What they did was they did not allow the converter's voltage transfer ratio to be, going to infinite, and we said that it limits the voltage transfer ratio in the boost converter, right? So that's an effect that you see in the boost converter. In the buck converter, they didn't study that initially because it's not as important. Because in the buck converter, what will happen is, as you see in this slide, here what they did was they didn't consider the effect of the resistance of the inductor. In this converter, they consider the effect of the voltage drops on the diode and the switch, right? So what's going to happen if you consider the voltage drop on the diode and the switch? Then they go through the same process. At the end, you have to find the voltage transfer ratio, right? They were looking at the voltage across the inductor when the switch is closed, voltage across the inductor when the switch is open, and then from these two, they were able to find the voltage transfer ratio, right? So they go through something similar here, but they consider the switch voltage drop, right? So the voltage on the inductor when the switch is closed, like when the switch is closed, the diode is open. If the diode is open, then the voltage across the inductor should be what? Supply voltage minus the output voltage, right? Without considering a switch drop, right? But if you consider the switch voltage drop, it's the supply voltage minus the output voltage minus the switch voltage drop, right? So that's the only difference to the voltage across the inductor in that case, when the switch is closed. When the switch is open, the diode is shorted, right? If the diode is shorted, the voltage across the inductor was 0 here, minus V output on the other side, right? So it was minus V output. But if we want to consider the forward voltage of the diode, forward voltage of the diode opposes the flow of current, right? So it's in the opposite direction as Vx. That's why it's with a negative sign here, right? So, right? I just want to confirm that. If this is a diode, my forward drop is opposing the current flow, right? V forward of the diode, right? So if I would like to find the voltage across my inductor, it's the voltage at this terminal minus the voltage at this terminal, which is the minus V diode, and then minus V output. Okay? So this is the voltage across the inductor when the switch is closed, when the switch is open. And then we look at the voltage transfer ratio, and the way we can do that is by knowing that the average voltage across the inductor is 0 over the switching period. So this is the voltage across the inductor when the switch is closed. It happens for a duration of D, duration D of the duty ratio, right? The device being on. Plus the area under the voltage curve when the switch is open, which is for the period of 1 minus D. These two areas have to equal 0, right? These two areas are equal to 0. This is the voltage across the inductor when the switch is closed, voltage across the inductor when the switch is open. This area, A1 plus A2, have to equal 0. Right? This area is when the switch is closed for a period of D of the full period. So D times T. And this occurs for D minus 1 minus D, 1 minus D of the full switching period, right? So this height times D plus this height times 1 minus D is equal to 0 because the T's cancel, right? So it's this height of A1 times dt plus height of A2 times 1 minus dt equals 0. The T's just cancel out, so it's the height times D plus the height times 1 minus D is equal to 0. So that's what they did here. The height times D plus the height times 1 minus D is equal to 0. And then they found the voltage transfer ratio. Without considering the switch loss, the voltage transfer ratio was, for the buck converter was what? V output is equal to V input times the duty ratio. Right? If you remember from our derivation of that, it was this, right? Now it's V output equal to V input times D minus all of this, right? What is the effect of that? Reduce the voltage even further, right? But I have a buck converter, so it doesn't really matter, right? That's why the effect on the boost converter was more important, because in the boost converter it actually limits the boosting ratio. But here it doesn't limit the physical phenomena I'm trying to achieve anyway, right? It's going that same direction, right? It's helping reduce my voltage. So I just have to consider that if I would like to go into that detail of considering the switch losses if I want in my circuit design. Yeah. Okay, so that's something to consider. Then the other thing we need to talk about is discontinuous current operation. So everything we've talked about before, all the design equations and stuff that were derived in the text were based on continuous current mode, right? Continuous current mode, and we're always referring to inductor currents being continuous, right? So anytime all the equations that have been derived in the text so far, we're assuming that the inductor current has some ripple content, delta I, and that the minimum value is always greater than the minimum value of I is always greater than 0, right? It's always greater than 0. This is I minimum, right? We were sort of designing selecting an inductor, starting from there, and isolating the discontinuous mode from the continuous mode. But we also said that there's nothing wrong with operating in discontinuous mode. It's something you have to do because sometimes you have no load across the power supply, because this is average current. This average current is sometimes the average current, again, depending if you're looking at the buck converter or the boost converter or the buck boost converter, this average current is either typically the input average current or the load average current. So for you to have input average current or load average current, that means you have a load in the circuit, right? There is a load that's in the circuit, yeah. So if you're operating at no load, then this average current is very, very low. If your average current is very, very low, and you want to operate in continuous conduction mode, what does that mean for your selection of capacitors and inductors? If you want to operate at the average current that's very low, what does that mean for if you want to make this continuous? If you want to operate in continuous mode, in this case, you will have to make sure that your ripple looks like this. Right? So you would have to reduce your ripple considerably to be able to do this, correct? Because here I'm still operating in continuous conduction mode, right? But what that meant is that I had to reduce delta I considerably. To reduce delta I considerably, that means I had to do what? Right? Delta I is ripple current, right? How do you size inductors? Inductors is equal to the value of inductor that you want in a circuit is equal to the area under the voltage curve, inductor voltage curve, divided by the delta I spec. So delta I is equal to delta lambda over L. So they are inversely proportional, right? So if you want delta I to be very, very small for the same switching frequency, you will end up with a huge inductor. The other alternative is to increase switching frequency, because if you increase switching frequency a lot, then this delta lambda will be small. Right? If you make delta lambda small, it's proportional to delta I. So you can make delta I small. Right? So you can make this small by making switching frequency very high, because this is the area under the voltage curve across the inductor. Or you end up with a large inductor. So either huge switching frequency or very large inductor. So you cannot afford that sometimes. Right? So since you cannot afford that sometimes, you will have to operate in what is called discontinuous conduction mode. Discontinuous mode, inductor current can look something like this during a switching period. This is IL. It goes down to 0 for part of the switching period. Right? This is called discontinuous conduction. It has an average value, very low average value. For example, it's a very light load. The average value is very low, so you will have an average value. Sure, no problem. But you're operating in discontinuous conduction mode. You did that because you don't want to increase switching frequency very high, or because you don't want to live with a large inductor. So discontinuous mode is a good alternative if you want to optimize your switching frequency or losses and the size of the power supply. But what is the goal or the physical phenomena that we still cannot break? We cannot break the fact that the average inductor voltage has to be 0 in steady state, right? So we cannot change that. I mean, the average inductor voltage has to equal 0. So the voltage across the inductor here will be a positive number. Voltage across the inductor here will be a negative fixed value, right? So if this is VL, right, IL is equal to VL is equal to L di by dt. So I L is equal to 1 over L integral of V dt. Right? This is a constant. The integration of it is a ramp. This is a constant. Integration of it is a ramp. It's the same thing we did before. And this area still has to equal this area. I did not draw them very nicely in proportion here properly, but they should be equal. So if this is a large value, if this is a wide, or this is a longer period of time, then this value would be, the height here would be smaller than here for sure. Okay, because the two areas have to equal each other. Because the average voltage across the inductor has to equal 0. The average current through a capacitor has to equal 0. Right? If you're going to operate these devices in steady state, which is where we're operating, then these physical phenomena cannot be broken. So I will use, so sizing of the inductors and capacitors will not change. Right? Because again, I still have L is equal to delta I, delta lambda over delta I. I have a certain ripple here. This is my ripple current, right? And this is delta lambda is the area under this curve, right? So I still can size it using the same fashion. Sizing the inductor graphically is the same way. It's the area. It's the same. I mean, it will not change. It's the area under the voltage curve, which is flux linkage, divided by your ripple current spec, right? So, and they do the same thing, but what will it change though? It's going to change the voltage transfer ratio. How will it change that? So remember we said that areas have to be equal. So the voltage, these are the areas across the. This is the voltage across the inductor when the switch is closed. For the buck converter, it's initially what? Switch is closed. It's the input voltage minus the output voltage. Correct? This input voltage minus the output voltage is occurring where? When the switch is closed. So it's the V input minus V output times dt. Minus the other area should be 0. The other area is where? The other area is the time duration between this point. Now the switch opened. The switch opened and the current fell down to 0. Fine. And this is the period where I will have voltage being negative across the inductor. Right? This is the problem now, because this is not 1 minus d. Remember before here, it was the derivation we had here. It was what? It's Vs minus V output times d, and then minus V output times 1 minus d. I no longer have the 1 minus d simplicity anymore. It's some time duration d, d1. This is happening during some time duration d1, right? So the switch is on for d. It's off for 1 minus d, I agree. But there's current flowing only until d1 of t. Right? So current falls down to 0 after d1 times t. Right? So this is how you will get your voltage transfer equation, not from the 1 minus d. Right? So these are the two areas that are equal to 0. So Vs minus V output times the duration of the switch is on minus V output times the duration when the switch is off and the circuit is conducting current. That's called D1. So this is the new voltage transfer ratio. So this is the new voltage transfer ratio for the buck converter, right? What don't we know here? We don't know D1, right? We know D. We know D from, that's the time when the switch is on. D1 I don't know, because that's when the current falls down to 0, right? So the textbook, there's a derivation that shows you that, and D1, for the current to fall down to 0, it's going to depend on what? It's going to depend on your load. It's going to depend on your switching frequency or inductance as well, right? So in the textbook they derived an equation for D1 that depends on, of course, your load, your switching frequency, the value of inductance you have in the circuit, etc., etc. Right? So they take that and substitute for D1 here, and then this is the voltage transfer equation for the buck converter in discontinuous mode. What was the voltage transfer equation for the buck converter in continuous mode? V output was equal to V input times D. Right? Now it's V output equals to V input times all of this. Right? This tells you that you cannot control the power supply in discontinuous mode and in continuous mode the same way. Right? It tells you that, right? I mean, no, it's behaving differently. It's behaving. You have an equation that's describing the behavior. That's fine. But it's behaving differently. So that's why it's always important to know when you're going to go to continuous mode or when you're going to be in discontinuous mode. To be able to sense that so that you can change your controller. The software that you write or the analog controller that you've devised for the power supply will have to change its operating mechanism, operating mode, because it's dealing with something different. Okay? I'm not asking you, I mean, the derivation for this, I don't care for you to memorize it or know the derivation. I just want you to understand the logic, right? The logic is average voltage across the inductor is 0, right? It's called volt-second balance across the inductor. Volt-second balance across the inductor means that the voltage across the inductor when the switch is on and the voltage across the inductor when the switch is off and the circuit is conducting current, right? These two areas have to add up to 0, right? And this is the equation that describes that. This equation has a new variable now that we have not seen before, right? It's not the duty ratio. It's not 1 minus the duty ratio, which is the rest of the period. No, it's part of the rest of the period. This part of the rest of the period we don't know because it depends on my load, depends on my switching frequency, depends on many things, right? So we had to find an equation describing D1 in terms of things that we know. We know my inductor, we know the load, we know the switching frequency. So the text derived an equation for D1 that we were able to substitute in the equation for the voltage transfer ratio for the buck converter. Okay, that's the logic I would like you to understand. And it's the same with the boost converter. We'll look at it now as well. Right? So we will look at the inductor current. Inductor current, we know that the average voltage across the inductor is 0. So the area positive plus the area negative will have to equal 0. And we will find the variable D1 in there because current is discontinuous. And we will find D1 in terms of D and the rest of the parameters of the circuit. Right? So all the parameters affect each other. So in this continuous mode, it's not simple anymore. Right? Because you change the load and you're changing your operating your control, the way that your power supply will respond is not linear anymore. Right? You used to change duty ratio and you saw the output voltage increasing. Right? V output was equal to V input times duty ratio. You increase duty ratio, output was increasing. Increase duty ratio, output is increasing. Decrease duty ratio, output is decreasing. But here, what's going on? It's a different curve. It's a curved relationship. It's not quadratic relationship. It's not a linear relationship anymore in this case. Okay. But as I said, whatever's constant is the fact that the sizing of the reactive elements does not change. I need to look at the voltages or these areas. After you look at these areas, this is the area this is delta lambda. This is the amount of flux linkage you're putting across the inductor. This is the amount of energy storage you're putting in there. Take that, divide it by your delta I spec, and that's it. Your delta I spec, you decide what it is. If you want to operate in continuous mode as much as possible, you will be decreasing that as much as possible. If you're going to live with a bigger delta I because this is what's practical to build a practical power supply that's operating mostly under load. It's operating mostly under load, then it's okay. Then keep delta I a little larger and it's fine. Right? You save on the size of the inductor and the cost of that. So it's a design consideration. But the sizing does not change, right? It's the area under the curve divided by the delta I spec. Does not change. So any questions on this? The only thing I added was this D1 variable. And I said that this D1 variable, it's derived in terms of the rest of the parameters of the circuit, and you just plug it into the voltage transfer equation that we know how to derive. And they will do the same so this is the Originally, the buck converter, as I said, we operated in linear fashion, right? You increase duty ratio, the output increases. Increase duty ratio, the output increases. In discontinuous mode, we operate on a curved performance. So it's different. It's not wrong or bad or good or whatever, right? It's just different, yeah. So you just have to make sure you consider that in your control. For the boost converter, same thing, right? So we look at inductor current. If inductor current becomes 0 before the end of the period, that means we're operating in discontinuous mode. When does it fall down to 0? After a duration d1 times the switching period, right? So again, how do we derive the voltage transfer ratio? We look at the volt seconds balance across the inductor, right? When the switch is closed, we had what? We had V input minus 0, right, across the inductor. When the switch is open, we had what? V input minus V output across the inductor, because when the switch is open, diode is shorted, and then this is the voltage on the other side of the inductor, right? So one side I have V input, and the other side I have V output, right? So I have V input for a duration of D of the switching period, and I have V input minus V output for a duration of D1 now, not 1 minus D. That's the only difference, is this D1 is not 1 minus D. Okay, the T's cancel, right? And then we end up with a voltage transfer ratio that looks like this for the boost converter, right? This is something we cannot deal with because we only can control the duty ratio of the switch. That's the only control variable. So I have to write the voltage transfer ratio of the boost converter in terms of the parameters that I know in the circuit. I don't know D1. So in the book, they derive a relationship that governs D1 and relates D1 to the rest of the variables that we know about. We know V input, we know V output, we know inductor, we know duty ratio, we know resistance, we know switching frequency, and then we take that and plug into the voltage transfer equation. Before, in continuous mode, I'll go back to the slide. In continuous mode, the input-output relationship of the duty ratio versus output relationship of the boost converter looked like what? Had no straight line here, right? It had no straight line. It looked like what? Let's go back to the boost converters here. So this was the performance of the boost converter, right? This curve going all the way to infinity. After you've considered the discontinuous mode, or in discontinuous mode, the performance is different. So I have a sort of a straight line at the beginning here that is different than the previous case. Good or bad is there's no good or bad. This is just how it operates, and you have to make sure you control it differently in discontinuous mode versus continuous mode. And this is the voltage transfer equation, input to output equation that we've derived here. After you take this and plug D1 here, you will find the relationship between V input and V output. Okay, you're not asked to derive that. I mean, for this discontinuous mode, you're not asked to derive that or go through the equations. It's take this, what they've derived in text, and plug it into the voltage transfer equation. Because at the end of the day, it's the voltage transfer equation is what we're after. Yeah. Right? I'm not asking you to derive it. Is it clear? And here it's the same. They're just reiterating the fact that the volt-second balance across the inductor has to exist. So this area has to equal this area, and that's how they were able to write this volt-second balance equation. Which from there they went and found the voltage transfer ratio. So and then sizing the inductor is exactly the same as well. It depends on the area under the curve and your delta ripple spec. So I didn't say anything new. We just introduced a new variable. This new variable was D1, and it does not equal to 1 minus D. That's all really. So this is really what I care about to talk about about discontinuous mode. Any questions about discontinuous mode? Again, it's an inherent characteristic of operating a power supply with a variable load. Right? If your power supply would only operate with a fixed load that never changes, you don't need to worry about this at all. But if your power supply's load will keep changing, you will have to decide how much time you operate in continuous mode and how much time you operate in discontinuous mode based on your switching frequency and inductor current and inductor value that you choose. You choose that. It will depend on size, cost, efficiency, all of these things combined together. I mean, I cannot tell you this is the best way to go for this application. You will have to, like the bonus question that I gave you, you will have to go through that. Do the whole thing maybe on a MATLAB script or a MathCAD script, and then change switching frequency and see what happens. Change the switches thermal resistance and see what happens. Change the MOSFET's RDS on, see what happens, right? Maybe it's best to buy a MOSFET with a lower RDS on than to add a heatsink. I don't know, right? There are too many things interrelated to each other. As you see, D1 now is dependent on many things. D1 is dependent on duty ratio, depends on switching frequency, depends on the size of the inductor, depends on your load, right? So I cannot tell you, okay, do this, do that, do this, do that. It will depend on your spec. You want something very small. You want something very efficient. You want something, and then you may not want. You may want two things versus the other two compromise, right? So it will depend on what you really want to do. So that's the end of chapter 6. I know it took a lot of time, but it's an important chapter. Yeah. So any questions on this? I added, I added stuff from chapter 10. I did not cover all of chapter 10 about losses and thermal design, but it was something I had to add to this part of the text, to this part of the syllabus. Yeah. So any questions on this? On the exam? Any questions? We will stop. Again, the exam will be until before our discussion of switching losses and thermal design. We will keep those for the final year. So if we don't have questions here, I'll start chapter 8.
If there are any questions on question 4?
Question 4 is fair after our discussion.
Afterwards, after we discussed it was pretty
Sure. So I did not make the exam yet, but again, I don't intend to make it any more difficult than the previous one. So yes, I intend to probably have maybe a true false, a multiple choice at the beginning, and then probably some waveform drawings, and then I would say something similar to the homework, problems similar to the homework, really. I mean, and that's what the last exam was about as well, yeah. So I advise you to make sure you look at the homework problems, understand them, try to identify the tricks in the different homework problems. I'm really not out there to make you feel bad or get a bad grade. Really, I would like to make sure that you understand the material and do well, actually. So didn't turn out as the way I wanted it to be last exam, but hopefully this exam will be better. So any questions on the material? Okay. So if there are no questions, I would like to at least get started on chapter 8 so that we have an idea of where we start. Final will be cumulative, yes. Final will be cumulative. So chapter 8 will be the inverters topic. So we have discussed so far, we discussed DC to DC converters. We discussed AC to DC rectifiers, right? We discussed AC to AC voltage controllers. I would not say power converters because there are many topologies. I think you guys are going to be exposed to a lot of the AC to AC converter topologies. There are many types that we will not discuss here or here actually, but the last sort of area that we want to discuss, or converters that we would like to discuss, are the DC to AC converters. And these are called inverters. Right? We discussed a little bit about inverter operation in our rectifiers topic, and this was a very special type of inverter. I mean, it's a thyristor-based inverter. I mean, they are used typically at very high powers because thyristors are very rugged devices that you can use at high power. So some very high power drives are driven by inverters that are thyristor based, right? Very high power, like 20 megawatt based drives, etc., etc. We will be talking more about PWM, pulse width modulated DC to AC inverters in this section, in chapter 8. Okay, so the objective is, of course, we would like to create as nice of a sine wave as possible. That's the final objective. We will be skipping. I know this looks like a lot, but we will be skipping a lot of stuff, and a lot of this will be things that we have to know. Just draw the circuit, draw some waveforms. So it's something. It should not be too much of a problem. Yeah. Where do we use these inverters? Again, anytime we want to convert from DC source to an AC load, like adjustable speed motor drives, uninterruptible power supplies, hybrid vehicles. There are many, many applications that, of inverters. Yeah. One of the simplest inverter topologies is something you are actually building in the project, which is the full bridge inverter, right? So you are building that with the purpose of creating DC at the end, right? But in the intermediate stage, you're creating high frequency AC, right? So we had you're building. You have our full bridge inverter. Looks something like this. You have your DC power supply here. Again, remember our trick that we talked about here. The way I would like to represent this is the same way I discussed the DC to DC converters as well. So I can represent this full bridge converter using this representation, simplified representation that I discussed when we discussed DC to DC converters. Right? I have a pole here, or an arm here that's oscillating that's moving between these 2 points. And I have one here that's also doing the same. I just happen to have the same DC voltage applied to this arm and same DC voltage applied to this arm. The other thing is we always said that here across these switches, which I represented using this sort of arm with 2 contacts, right? Across them, I always have a fixed voltage, right? A stiff voltage. Remember we said in the buck converter, the stiff voltage is the input voltage. In the boost converter, the stiff voltage is the output voltage. In the buck boost converter, that stiff voltage is the V input minus V output, right? Here, I have the same thing. I have a stiff voltage here. That's always equal to this VDC, or the V input voltage. And at the output, I always had in the buck or the boost or the buck boost, I had the switch current going through an inductor, right? And it's the same here. I can draw this as half the inductor here, half the inductor here. They're in series anyway, right? And then this is my load for my inverter. This load can be a resistive load, so I can put this load here. It's coming. There's an inductor here, and I drew an inductor here, and then I can draw a resistor here, and maybe I put a capacitor as well. I can, right? Or maybe not. Right? Whether or not I put a capacitor will depend on how much ripple voltage I want to maintain across my load, right? So it's up to us later to decide if you put a capacitor or not. But if I want to select the switches that I put in here, I can go back to slides of the first chapter, right? The first chapter slides. What do I see here? Current is in this load. I want to create AC current, right? I want to create current that is going to go into this node or out of the node, right? So it's going to go into this node or out of this node, right? But the voltage doesn't change polarity, right? So if we go back to this chapter 1 slides, that table that we had with how to select switch architecture, right? I have current here, positive, and current here, negative. Voltage is only in one polarity, right? My voltage here does not change polarity, right? My voltage is always in the same polarity. My current is changing, is either positive and negative, right? So I have to consider this architecture or this selection of devices as well as this selection of devices, right? So I have to find a way to combine these two, right? So how can I combine these two? You can go about it step by step. I want to combine the top 2 switches either in series or parallel. I want to combine the bottom 2 switches either in series or parallel. That's the only options that I have. If I take this switch and put it in series with this diode, I cannot do that because this switch is pushing current in one way and this diode is pushing current in the other way. If you put them in series, then you will have a switch here and a diode here. This wants to push current this way, this wants to push current this way. It will not work, right? So the only way to combine these would be to put the switch and the diode in parallel. we do that, then we can allow current to flow this way in a controlled fashion, and this way in an uncontrolled fashion. Okay, but at least I can have current flow in both ways. And I have to make sure that in this reverse direction, there's another switch that allows me to control current flow in that direction. Right? And that, if I do that, then I have controlled current in all directions. Right? So that's the objective here. So now I can take this architecture that I came up with here and substitute it with devices if I want to. Before doing that, let's just see what's happening here. So this is V inputs. If I have this top arm connected to this node 1, 2, 3, 4, this arm on the left and arm on the right, the arm on the left connected to node 1, and the arm on the right connected to node 4. What's the voltage across my load? What's the voltage across my V output? Exactly. So if I have this arm connected to point 1, this arm connected to point 4, I've taken this load and placed it across Vn. How about if I take this arm connected to point 2, take this arm connected to point 3? What is the output across what is V output equal to? Is it Vn or minus Vn? You flipped it, right? So initially you had this case. This is V output.
You said you had two switches in there that control the current, right? Well, not a back feed.
No, these are now ideal switches. For now, there's this is an ideal switch. This is just an arm that's flipping now. So when I had this arm connected to point 1 and this arm here connected to point 4, this was how my circuit looked like, right? And now if I now make this arm connected to point 2 and this arm connected to point 3, then the circuit would look like this. Current here was flowing this way. How about current here? The opposite way. Right? So in one configuration I'm putting V input, in the other configuration I'm putting minus V input, right? If this is the polarity of V output, I flip the polarity of V input across it. Right? So I have V input or minus V input. Do you agree? Okay. Another way to look at it How about if I do this? How about if I connect this arm to 1 and this arm to 3? What do I have across my V output? This arm to 1? Yeah, I would have 0. How about if I have this arm connected to 2 and this arm connected to 4? 0. So this converter topology allows me to get an output voltage. V output is equal to V input or minus V input or 0. Right? So I can get 3 levels of output. Okay? I can think of this in a different way. That's something more like what we've been discussing in DC converters, right? So if I have this configuration, just this half of it, just looking at half of this thing, okay? This is operating with a duty cycle of D1, right? And this is my V input. We said that the average voltage I see here is always going to equal what? What's the voltage I will see here? It's either V input or no, 0. This is 0, my reference, and this is V input. So the voltage here is going to be between 0 and V input, 0 and V input, 0 and V. So its average value is going to be between 0 and V input. But what is it equal to? In terms of D1? Exactly, duty cycle times? Exactly, so it's equal to duty cycle times Vn. Right, so I have duty cycle times Vn coming from this side, right? I would like to look at V output. If I want to look at V output, I have V output here. V output is I want to know what my V output is equal to. Then I have to look at the voltage here minus the voltage here to see what my V output is, right? So now I looked at the left-hand side. My voltage is D1 times V input. Assume now that I don't allow for this zero state. If I don't allow for this zero state, then I'm always going to operate with how? I'm always going to have this arm at 1 and this at 4. Or this at 3 and this at 2. I will never have this 1, 3, and 2, 4 configuration, right? So let's now, for now, just forget about this zero operation. If I do that, that means I'm operating this other side of the other side of the converter. So let me draw the other side of the converter here. Here I can draw the same V input across it, right? And here. I don't want to know what my voltage here looks like. This is the same V input, right? So what is the average voltage here? What does that look like? Exactly. 1 minus D1, which is the same duty cycle, because I said that if this is the top, this is the bottom. This is the bottom, this is the top. So they're opposites of each other. So for the switching period, if this is D1, this is 1 minus D1. It's 1 minus D1 times same V input, because they're the same. They're the same, right? They're connected to the same DC input, right? So on one side I have D1 times V input. The other side I have 1 minus D1 times V input. So what is V output? V output is the difference between the two. So V output is equal to D1 times V input minus 1 minus D1 times V input. So it's equal to what? D1 V input minus 1 V input plus, right? D1, right? So it's okay. So 2D1 V input minus V input, right? Or V output is equal to what? V input 2D1 minus 1. So if duty ratio is equal to 0, what's my V output? Minus V in, exactly. If duty ratio is equal to 1, what is my V output? V in, right? So my V output will range between minus V in to V in, depending on the duty ratio, which confirms what we were talking about here with this flipping business, right? So you know you can now derive it easily, and we can do this for the half. So this is called the full bridge converter. The voltage, the range of operation, range of output voltage for the full bridge inverter is minus V input to V input, right? That's because I chose these to be complementary, right? If I am to include this zero operation, right? How will I write this? How will I write this? Can I write this as 1 minus D1? No, I will have to write this as D2 times V input. And then the output voltage will be, you know, D1 times V input on this side, minus D2 times V input on this side. So the output voltage will be V input D1 minus D2, right? And in this case, if D2 is 1 minus D1, then I will operate only between I can only operate between minus V input and V input, right? If I want to get zeros, I can make it 0. I can make these two duty ratios the same, right? If I make this 0.5 and this 0.5, then I can get a 0 as well, right? If D2 is 1 minus D1, I will operate between these 2 points. If I want to get the zeros to function, then I can operate in this fashion. What is the benefit of the zeros or not? We will talk about that next time. But I just want you to get a feeling of the operating range, and then we can do the same thing for the half-bridge inverter. There's something called the half-bridge inverter topology, and the half-bridge looks like this. These are two capacitors, and this is my same representation. So this is operating with D1. What is the voltage here? Average value? V in times D1. What is my voltage here? This is the capacitive voltage divider. So this is V input here. This is V input over 2. Two capacitors across the DC supply. It's a capacitive voltage divider. This will be charged to half. This will be charged to half. So my output voltage now is equal to what? V in times D1 minus times V in over 2. Right? This is my output voltage. I'll take output voltage between these two nodes. You can tell me next time what's the range of operation for the half-bridge inverter, and then we'll continue next time. Okay, so we'll stop here. We'll continue with inverters next time, and hopefully you'll do well in the